This talk is the logical, say, continuation of what I presented in the previous lecture, even if here I will not focus on technological aspects, but I will focus on the algorithms. I already started commenting the importance of being able to characterize the effect of the environment of our system, and then conversely from our system to the application. Now we are going to see why it is relevant to explicitly deal with this non-stationary behavioral systems, and that's the reason why we are talking about the learning in non-stationary environments. We will address it from two different perspectives. The first one refers to what to adapt, because in the learning and stationary environments, we have a form of adaptation, means that we have to adapt our classification system, regression system, let me say, broadly speaking, our machine learning systems over time. So we have to adapt it, and we have to understand what to adapt and when to adapt, meaning that we have a temporal evolution and, let me say, a spatial evolution about what to do when we realize that something is changing or evolving. Then I don't know if I will have time to do that, but I will mention three specific active areas of learning in non-stationary environments. I will try to focus on the specific one, which is the one associated to learning in learning convolutional environments, in learning convolutional neural network in non-stationary environments. And then it is really worth exploring the area of federated learning. And then I would like to say a couple of words about a forecasting as a service perspective for time series based on learning in non-stationary environments. But so let's start with a toy example, where this toy example exactly refers to toys, meaning that here we have, this is my son some years ago, I'll say many years ago. He was trying to explore a very tough classification problem to understand whether each specific object was able to pass or not through that basket. And that was the tough classification problem he was trying to address. Here, the perspective from the learner, so from the machine learning expert, is the ability to model this problem as with a machine learning perspective. Obviously, the easiest way to address this problem is to try to create a physical representation of our object, a physical representation of the basket, and then having this physical perspective, so the physical model of object and basket, we can understand, we can evaluate whether the object is passing or not without even trying it. But the machine learning perspective we have forces us with a brute force approach, where the brute force approach means that we try data-driven whether objects are passing or not, and then we create a model on this. We create a model that allows to understand that that specific object is passing, while that specific object is not passing. The learning goal here is to create a relationship between features extracted from object, dimension, I don't know, size, first, second, and third dimension, and the shape of the basket. This is a very general approach. Here I will try to be faster and then to focus on the goal. But if we think about all the learning problems that we have, whatever the learning problem here is that we have a data generating process P, which is generating data over time. These data are used to estimate whatever model we have in mind. It could be a classification model, it could be a probabilistic model, it could be a dynamic model. So we use data to estimate model. This model is then used in an application, where the application is recognize that that is a person, or to forecast the weather we will have tomorrow. And that's all. That's what we do with our data. Data are meant to create our models, and then models are used within application. We will come back then on this later on. But if we model our problem within a statistical framework, and these are things that we all know, but I will add a specific comment at the end just to emphasize the perspective that we will use during the lecture. If we consider the general statistical frameworks, which is based on a process generating the data G, which generates data which is Y, where G is a nonlinear function receiving an input X, and eta is some noise which introduces the uncertainty in the measurements. We have a set of couples which we call the typical training set, X as Xi and Yi. So if we have n couples, we have from X, Y, X1, Y1, Xn, Yn, and we use this training set to model Gx, which is a priori unknown, by considering a parameterized families of model F with the parameters theta, X is the input. We want to identify the values of theta, so of the parameters, which allows to minimize, this is a regression, so the reconstruction error. Okay, so this is the scenario that that we have. F is, for example, a neural network. G is an unknown nonlinear function. We want to approximate F with G. This is, we say, state of the art. But which is the underlying assumption here that we have to take into account, and often we neglect it? Let me say, the implicit approach here is that the goal of the learning is to build a model which is able to explain past data, Zn, so our training set, and able to explain also future instances, which are provided by the data generating process. This is the underlying assumption, because we create our model on Zn, and then we estimate the parameters theta, minimizing the reconstruction error, and then we are expecting that what we train during the training phase will still hold even during the operational life, because this allows us to keep this sentence, so explain past data and future instances. But this does not always hold in the real world scenarios, where we have a discrepancy in the statistical distribution of the data between past data and future instances. So if past data and future instances are not sampled from the same statistical distribution, this means that what we are seeing here is not true. And in particular, say, the larger the difference between the statistical distribution of the training set and the operational phase, see, the larger the error that I will face with the model that I train on during the training phase. Why? Because we, as a machine learning perspective, we typically assume that the system is time invariant. Time invariance, which often is called stationarity, often it is assumed IID, meaning that the process is identically independent and identically distributed. This is typically assumed in the related literature, but this rarely holds in the practice, because we might have a gradual concept drift, meaning that we are things that slowly evolve over time, or we have abrupt concept drift, or aging effect, meaning that the interest of users might change over time. If you think about, let's say, in last year, 2020, when we had the COVID-19 pandemic appearing, I don't know, in Europe or in Italy, it's not difficult to understand that all the forecasting model, for example, in the forecasting of stock markets, forecasting of selling of goods, forecasting of activities of users, suddenly became useless, because the world changed at some point, and then this point made us understand that our IID assumption on the data was suddenly and unpredictably not operating, not true in some point of our operational phase of our system. So there are different sources of, let me say, evolution. We have aging effect. We might also have faults, malfunctioning in the system, introducing variations with respect to what trained and what explored. This is something that we have to take into account while designing our system. So if this is true, which is the effect that we are seeing? Let me make a concrete example. Let's assume that we designed a system to recognize the presence, for example, of the people in a critical area of, I don't know, airport, of a factory, of whatever. So we had the camera, we had the picture taken from the field. We had a training set. We training this training set. Sorry, we use the training set to train our convolutional network, whatever network you have in mind. Then you find the best network and you say, okay, I found my model. So this is the model explaining the presence of a person. But at some point, while the system is working, so while the system is operating, I have some dust which are coming on top of the lens. So at some point, the images which I'm acquiring are slightly different than expected because maybe they are darker, or the scattering of the light is different. Or I designed a system to recognize faces or to allow people to enter, I don't know, in a door, for example, a smart doorbell or something similar. But at some point, I start having a mustache, or I'm wearing a hat, or you have new glasses. These are sources of uncertainty which cannot be considered within the training set. And so the effect that I have is that the model that I previously trained is becoming obsolete, meaning that it is no more, it was effective, but now it is no more effective than expected, meaning that I need to update my model because perturbed, incorrect, or missing data can have an effect on the model. But we have always to keep into consideration that the model itself is a part of the application. So if the model is used to detect the presence of a person and then raising an alarm, or to recognize the owner of a house and then opening the door, if the model is not working properly, then this means that we might have a potentially catastrophic effect on the envisaged application, which is using data processed coming from the field. So this is exactly the problem that we have to face, because we train a model, we understood that the data generating process P might evolve over time due to faults in the sensor and the actuators, aging effect, or change in the environments. This means that our model must evolve over time. So we have to adapt it over time and being able to track the evolution in the data generating process. So which are the sources of uncertainty? So we are the sources of evaluation. Here we can decouple the word from two different perspectives. One perspective, it's called stationarity, meaning that we say that a process is stationary if the generated data are IID, so are independent and identically distributed realization of a unique random variable whose distribution does not change over time. So the stationarity hypothesis is the hypothesis that it is implicitly or explicitly assumed in, I would say, 99% of the machine and deep learning models which are in the literature. So these models assume that the process is IID. They do that explicitly or implicitly. Whatever it is, they are assuming that the process does not change its statistical distribution over time. We have to weaken this assumption of stationarity because we have to weaken the fact that the data generating process do not evolve over time, but it might evolve over time. And we have to take this into account in updating our models. And then we have the time invariance. What is the time invariance? It is a concept which is similar to stationarity, but it refers to dynamic system. Dynamic system implicitly take into account time. Because if you consider this dynamic model, here you see that yt is equal to a1 yt minus 1 plus a2 yt minus 2 plus eta. Here you see that time is taken into account, because you see that we have yt minus 1 and yt minus 2. But the model is not changing. What do we mean that the model is not changing? The parameters of the models remains stationary over time. So this is what we call time invariance. We say that the output does not explicitly depend on time, meaning that the parameters of this model are not evolving. And one could say, okay, but how can we design dynamic models whose parameters evolve over time? It's quite easy to do that. Instead of having constant values, we replace A1 and A2 with the parameters that have an evolution over time. So we could let the parameters evolve over time, as in this case, because, for example, here we could add a component such that we can let the parameters of our dynamic system evolve over time. And this is a system which is not time invariant. So we have to take into account both perspectives, meaning that it's not just a matter of time, okay? And in stationary, time has not an effect, because if the process generating the data does not change its statistical distribution over time, does not have an effect. And we say that the process is stationary. But we could also say that the process is time invariant, in the sense that the process generating the data could have or could take into account time, but the structure of the model, so the parameters of those models, are not evolving over time. Okay? So let's try to understand how to deal with this time invariance and, let me say, stationarity from the two different perspectives. The perspective is the fact that we need to adapt. Adaptation is how we manage variations in the data generating process over time. Because the traditional assumption is that the process is stationary or time invariance, but in a non-statistical framework, we need adaptive solution. So we need our system to adapt over time. And here we need to understand how and when to react, where how to react means that we have to do something. And here it is associated to what? What do when we detect that there is a change? And here we have three different families of solutions: instance selection, instance weighting, and multiple models. We will explore them in details later on. But this is how I react. But then it is important to understand when to react, where when is associated to, okay, I realize that there is a change. Do I have to react immediately or not? Or I don't care about the change. I'm just updating. Whatever it's going on, I just update my models with the data which are popping up from the field. So let's see these two different approaches in detail about the what and about the when. What? Here, as I mentioned, we have instance selection, instance weighting, and multiple models. Let's start with instance selection. Which is the idea? The idea is that we are receiving data which are coming over time. So at time t, I receive x, t, and y, t. At time t plus 1, I receive xt plus 1 and yt plus 1. So I have data which are, just to simplify things, assume that we have supervised data which are arriving over time. At time t, I have a training set which is storing all the data which arrived up to time t. So at time t, I have the data which arrived from time 1 to time t, and this is the training set which allows me to retrain my model over time. But at some point, at time t plus 1, I realize that there is a change. So I realize that there is a discrepancy. Then we will see how we can do that. But I realize that there is a discrepancy. And this discrepancy is detected by means of statistical hypothesis test, change point methods, and change detection test. And we will explore them in detail. So here, let's assume that we have an oracle. Say, hey, please take into account that there is a change. How can we react? Okay, if there is a change, this means that at some point in time, we had a change in the statistical distribution. So this means that I have to discard some data. Discard some data means that I have my training set. I will take only the last portion, the last in time portion of the training set, and I will discard the rest. Where to keep and how to do that, it's not easy, but let's assume that we say, okay, I keep only the last 100 samples. I keep only the last 10 samples. Or I want to estimate, and then we will see how to do that. We will estimate which is the starting point of the change. So say I detect a change now, but in my opinion, the change started, I don't know, 2 days ago, because it is an aging effect in the sensor. So I will discard all the knowledge are coming before 10 days ago, and I will keep only the last 2 days of measurements. So in this way, we have an adaptive systems that rely on a window, over the most recent training samples that will allow me to update my model over time. This training window could be fixed in the size, or could be dynamically adapted according to the content. And this means that I want to adapt the window length over the latest samples, where the goal is to maximize the accuracy. So instance selection means that we are selecting some of the samples, and in particular, I will keep the recently acquired samples. Instance weighting provides a different point of view. Here, the goal is that I don't want to select only the recent subset or subsequence of samples, but I want to keep all of the training samples. I want to keep all of them, but I want to be able to weight them in a different way, meaning that I will keep all the samples, but all the training samples suitably weighted will be considered. Meaning that if I am in a scenario where the data generating process is not evolving over time, so it is stationary, all the training samples are equally important, meaning that I will not focus on the most recent part or in the other parts in the past. While if I detected there is a change, then I will give more importance to the recently acquired samples, where the training samples might be weighted according, for example, to the age, meaning that the most recent samples will have largest importance, while the older samples could be maybe less importance unless they provide a relevancy to the current state. And this is an interesting point in terms of instance weighting. Why? Because in instance weighting, what I can do with respect to instance selection is that I can reactivate some of the previously acquired samples. Because if I'm introducing a recurrent concept, meaning that maybe I'm moving from day to night, but then during the next day, I will go again to night to day, and then I will go on, I move to day to night, it is clear that I have a change. But if I'm re-entering in a previously explored state, then I want to keep all the previously acquired samples associated to that state, okay? And I can do that with instance weighting, or as we will see, by explicitly taking into account the recurrent concept. In a simple instant selection mechanism, I just discard and I keep on training from scratch. That's the reason why in instance weighting, I can introduce a technique which is based on relevancy to the current state of the process in terms of the accuracy on the last batch of supervised data. So instance selection, I'm selecting a subset. Instance weighting, I keep all of them, but I will weight them in a different way. And then I have multiple models, where multiple models is exactly the concept of ensemble learnings. Ensemble learnings, we know that it provides several advantages in terms of reducing we mentioned before the bias variance trade-off with the instance, with the ensemble models. I'm trying to increase the bias and reduce the variance at the end. Here, these multiple models have the idea not in a traditional ensemble approach, meaning that they are providing different point of view of the same data generating process. Here with these multiple models, each models provides a specific view on a specific, let me say, time window. So each model is trained on a given subsequence of data. In this way, we have an ensemble of classifiers that at time t are able to provide I don't know, an evaluation, and then we average the results and so on and so forth. But here we have that the output of these ensemble are combined by means of a voting or weighted mechanism, and each model is created at runtime. This means that if we detect that there is a change at time t, what we can do is that we introduce a new model, a new classifier, a new regressor, a new predictor. And this means that from n model we go to n+1. But obviously, I must also have techniques that allows to also reduce the number of models. So I want to maybe remove the one providing the lowest accuracy, or I will remove the oldest one. So I have different techniques that I can use for the pruning. But here, the point is that a new model represents a new state of the process. And according to the amount of data that I receive, I create a new model, and then I will let it operate within an ensemble. So instant selection, instant weighting, and multiple models. Advantages and disadvantages of these solutions. The instant selections, it is typically characterized by the lowest complexity, because we keep only a subsequent of the training set, and this allows also me to reduce also the dimension of the training set. I can put a cap on the amount of data that I can store. For example, I say I keep a training window on the last, I don't know, 1,000 data, 10,000 data, whatever. I keep a cap, and then I want to satisfy it during the operational life. Which is the drawback of this approach, is the fact that we have fixed windows are, and in fixed windows, it is always difficult to set how much fixed, so which is the value that I want to use. And then I might have heuristics techniques that allows me to adapt the window size. The problem with instant selection is that I'm introducing forgetting mechanisms, because as I mentioned, if I'm moving from day to night, and then I say that now during the night, I will remove all the data which are associated to the date. In the instance weighting, here I can use, let me say, rather low computational complexity here, because I have just to use weighting mechanism. And the advantage is the fact that I can keep all the training data during the operational life. And this is particularly useful for a current model, as I mentioned before. But then, again, I need to identify some heuristics to sample, to define weights for the sample. And I have problem in complexity and memory demand, because I'm keeping the full training set for the processing. As regards to the multiple models, I typically create a new model for each new bunch of data. Every, I don't know, 100 samples, I create a new model. Every 100, 1,000, whatever, I create a new model. But obviously, this introduced a not negligible computational complexity, both during the learning phase. So because I have to create a new model to learn a new model on the fly, and during the operational life, because I have to keep several models which are running in parallel. This means that instance weighting and multiple models are typically, since they are characterized by larger complexity than instance selection, in embedded edge AI, typically the instance selection is the solution which is typically considered for the learning during the operational life. Okay, this explores how to adapt, but then we have to move to the crucial point when to adapt. It is interesting to note that in something which is evolving over time, the when is sometimes more important than the what, because the when allows me to adapt quickly and to maintain the performance. Because if I define it, I'm using very effective adaptation techniques, but then I'm not able to understand when to apply these techniques, then my powerful adaptation techniques becomes useless. So when is the crucial point, is the crucial question. When can be decoupled from two different perspectives, which refers to passive solution and active solutions. Let's see them in details. In passive solutions, we continuously update the model without the need to detect the change. This is a very interesting perspective, meaning that we don't care about what's going on in the data generating process. We just receive new data, we update our models, we create new models in the ensembles, but we are not really interested whether there is a change or not. This is it is an interesting point, because we are just said, okay, I want to understand when there is a change. But if I'm continuously changing, if I'm continuously adapting, it is like that we are not truly interested in there is a change or not. So I receive a new data. Okay, it is equal to the previous one. Okay, I'm just updating, just improving the performance. But if there is a change, I keep on updating itself. So it is a form of adaptation, but it is a form of adaptation that do not require an explicit detection of the change. Let's assume that every, I don't know, 100 samples, you take a model and then you add this model to your ensemble, fine. And you do that regardless of the fact that there is a change or there is not a change. Okay. So in this way, I'm trying to keep track while updating the parameters. But obviously, this increases a potential complexity because not all the solutions, not all the technological platforms allows you to continuously update. And that's where the active solutions come into play. Because in the active solutions, you are not continuously adapting. You adapt only when needed. So if you train a model and then this model is still valid over time, there is no need to update it. And where valid could be associated to, I don't know, to the accuracy you have. If your accuracy is remains stable over time, great, there is no need to update. Because if you are updated, you might increase the accuracy or you might get stuck somewhere and you are just losing energy and computation to update something where you are not truly required to update. The active solutions relies on triggering mechanism that allows you to identify the change in the process and react accordingly. Okay, and here the most popular triggering mechanism refers to change detection, meaning that we are sequentially analyzing data which are coming over time in order to detect when to change and then adapt only in that specific case. So let's see these two approaches in details. The passive approach, here we have a general idea. Let me remind you that the passive approach is refers to the scenario where you are continuously receiving data and you are continuously adapting your model over time, regardless the fact that there is a change or not. You can do that by means of a continuous adaptation, where the model parameters are updated every time you are receiving the data. This allows you to maintain an up-to-date model at all times, because I mean you are continuously adapting. So the model is the best model that you have while you are adapting it, and it has also an additional advantage. And this advantage is associated to the fact that the passive approach, not requiring on detection mechanism, they are robust to the fact that a detection mechanism is not able to detect it. Let me rephrase this because I will comment this then in the active part. If I need to understand that there is a fire because I have to raise an alarm, and at some point I'm quite confused and I'm looking somewhere else and I'm not promptly able to detect that there is a fire, then I'm introducing a delay. This delay has an effect on the fact that I'm not able to effectively detect an alarm. Or on the other hand, and this is a false negative, on the other hand, if I continually saying there is an alarm, there is an alarm, there is an alarm, this is a false positive detection, and the adaptation continuously trigger, but it is not useless. So it is completely useless. So it is not useful. This means that I'm just losing accuracy and I'm doing unnecessary operations. So false positive and false negatives are associated with change detection. The passive approach can overcome these problems because they do not have change detection. They continuously update, regardless of the fact that there is a change or not. This has some advantages, but as we will see, it has also some disadvantages. Let me show some examples of passive approach. And the passive approach is exactly what you have in mind for online incremental learning. Where in incremental learning, we can imagine that we have some data which are coming over time. I can compute a loss function, and I update these the parameters of our machine learning models, neural networks over time by obviously evaluating the effect on the parameters of the errors that we introduced on that specific value that we received over time. This is the classical scenario of online incremental learning. We could do that for one specific sample. We could do that for batch learning, where we update the parameters not for one single value, but for a batches of data. But here it's like we say that we are continuously the training in a, let me say, in an incremental way, even when we finish the training from our training set. This is exactly the concept of passive learning. So as you can see, we have the environment or the user, which is generating some data. Then we have the adaptation phase, because these data are used to adapt their models. And then this information and then used by the application. From the technical point of view, we use this in particular in the ensemble-based methods, and I already mentioned this when we talk about multiple models, because the ensemble-based methods are particularly suitable for learning in association environments following a passive approach. Why? Because every given amount of data, I create a new model. In stationary condition, think about this. Every 1,000 samples, every 100 samples, you create a new model. And in stationary condition, this is exactly like creating an ensemble. And we know that typically the ensemble-based approaches are more accurate than a single classified-based systems. They are able to incorporate new data into classification models because you are just adding a new item in ensembles. And they also provide a natural mechanism to forget irrelevant knowledge, because I'm just removing one item from the ensembles, and I automatically integrated a forgetting mechanism in my model, so being able to adapt my model, my ensemble models over time. So ensemble-based mechanisms, they have a huge literature in the field of learning in association environments, because they are really able to be very flexible in dealing with adaptation and non-stationary environments. Why? This is how we implemented. Over time, we received a set of data, which are S1, ST. These are batches of data. We add an expert, whatever the expert is. It could be a classifier, regression, and predictor to our family. We update the weights, because we have also, you have to remember that in ensemble approach, we have to understand how to weight differently the set of models that we have. And then we make a prediction of what's going on in the future. So we make a prediction on the next set of data. So we predict ST plus 1. And then you can measure the loss between what we predicted and what we measured. And this forced us then to we compute the loss, and then we can update the weights, and so on and so forth. So we add a new expert, we update the weights, and in this way we are creating a cycle where we have where we are able to adapt our ensemble models over time. Probably one of the most popular algorithm is SSIE, which is the acronym of streaming ensemble algorithm, which is one of the first ensemble approach which has been provided in the field of learning in association environments. Which, sorry, I forgot to say that learning in association environment is often also named learning in presence of constant drift. They are absolutely equivalent in terms of notation. Learning in association environments and concept drift, they both represent the same type of approach. Here we add a new classifier as a new batch of data is coming. Classifiers are removed as the ensemble reach a predetermined size. So we say, for example, we take at most 10 or 50 classifiers, and then when I fill, or my, let me say, the room for my classifiers, I will remove some of them. And then I'm asking myself, which are the classifiers that must be removed? There are 3 figures of merits which can be considered. I have to consider how accurate are these models, so I can remove the one providing the smallest accuracy. I can also take into account the age of these classifiers. I will try to be more conservative in the, let me say, younger classifiers. And I will try also to remove the classifier which contributed less in our voting mechanism or in our weighting. These are figures of merit that I can consider. This was one of the first approach which has been proposed in the literature. And then we had extension associated to online boosting mechanism, which are able to introduce this streaming ensemble within boosting, as well as a dynamically weighted majority, aiming at extending the weighted mechanism also to dynamic online learning algorithm, as well as other approach, for example, based on random forest, where I want to reduce some trees or to remove some trees according to the content which is provided in the creation of the output. You can find all the references at the end of this presentation, but here the crucial point is that these represent extensions of variations of traditional solutions, for example, random forest or boosting or bagging, being able to take into account the fact that the data generating process might evolve over time. One specific and well-known solutions is the Learn++ association environment, which is an ensemble-based approach which applies a time-adjusted loss function, being able to jointly consider accuracy and time to keep the classifiers which are not which are performing well in recent times and not just the most recent one. And this is interesting because according to what we define for in recent time, you can also keep classifiers which were very accurate, but not recently, maybe some times ago, because I'm expecting that I will reactivate those classifiers recently. And here we have classifiers that performed poorly a long time ago, could be reactivated because, for example, we are considering a recurrent concept or cyclic drift. Okay, before moving to the active learning, I saw that there is a question coming from Salfayumi. Okay. Passive learning, is there a guarantee that the NN will converge while we train it online many times? I mean, that's yeah. This is the comment is, can we provide some guarantees that we have some, are there theoretical guarantees that allows us to say that in passive this incremental learning allows us to go somewhere in terms of convergence instead of diverge over time? That's a crucial point. There is some theory that tells us that according to how I define the decay rate of my learning algorithm, I can converge, or I have some properties that guarantees the convergence. Obviously, I have also to be very careful in how I modify the decay mechanism, because this introduces the so-called plasticity stability dilemma, meaning that the larger the plasticity of my learning algorithm, also the smaller the stability. Let me rephrase this comment. If I have a classifier which, or if I have a model which is able to adapt very quickly, because maybe I give more weight to the last training samples, I'm very plastic in the sense that I'm really able to react and to track the evolution. But the stability is what I'm paying in terms of where I'm going. So that's exactly the point which has been raised in this question. So the stability plasticity element is exactly the trade-off that you have to balance, because the larger the plasticity, we say the smaller the stability, and the opposite. the larger the stability, the smaller the plasticity. It is a trade-off, obviously, and the point is that I'm able to play with this trade-off if I'm able to recognize where I am in time, meaning that if I am in a stationary environment, I don't want to be plastic, but I want to be stable. Okay, so I want to converge. So if I'm able to, if I can measure that I am in a stationary, I want to quickly converge. It's like that I'm using in time the batch learning that I can do with our training algorithms. While if I'm able to recognize that I am in a non-stationary situation, then I want to be plastic, because I want to quickly adapt to the new changes. And that's the reason why I can tune this trade-off, stability and plasticity, by relying on active learning, where this active learning allows us to provide information about an event, provide information about what's going on. Okay? Did I answer your question, Safa?
Yes, thank you.
Okay, let me see. Lucas questions. How do you know that the labels associated to your incoming data? How do you know the label associated to your incoming data, if those data are the one that you have used to make your prediction? Okay, that's okay. Okay, let me go. This is a very important question. So then I will answer the other question from Luca. I'm not saying that I'm using the labeled data to train my system. That's a completely different story. What I'm saying is that typically the non-stationary environments or concept bridge follow the so-called test and train approach. What does this mean? This means that I received some data, and on this data I have just the input. Then I classified it, I provide the output, and once I provided the data, so the testing phase, then I have the labeled information, so the supervised information, such that I can then update my model. Okay, it's like that. It is an interaction with the expert, but the expert provides the information only after the system provided its own evaluation. Okay, Luca. So I'm not saying that I'm using self-trained data, which does not mean that it is impossible to do that. There are solutions present in the literature that can support this. This is particularly true for semi-supervised learning in a session environment. Well, this semi-supervised refers to the fact that I have partially supervised information, so not all of the data are supervised. So if the supervised information is scarce, I try to use semi-supervised information. So I'm trying to do self-supervising, and this self-supervising is used to integrate information. But this, it's quite dangerous in the sense that if I'm incorrectly classifying the samples, then I'm introducing mistakes in the training base. So I must be a lot of attention, must pay a lot of attention in making this a semi-supervised approach. Okay, Luca, did I answer your question?
Thank you. Just to clarify, I didn't understand the approach of test train. That the one that you want.
The test and train is the following. The system which are operating in the learning in session environments typically assume the test and train approach, meaning that at first you receive the input, so the X. Then the system provides the Y hat, so the prediction. And then the expert provides the supervised information. So you are not receiving X and Y, so input and output at the same time, because otherwise your prediction is useless, because you already have the supervised information. Okay, and you can do that irregularly over time. So you can do that, I don't know, you receive the one supervised information every 5 samples, every 10 samples, every 100 samples. Okay, Luca?
Okay, thank you.
And as regards the second question, the second and third question, this is exactly one point that is present in the second part of the slide, those that I was not able to explore today. But typically, this training is done on the cloud, not on the device. We are currently exploring the scenario to do on-device learning, on-device incremental learning. But here the point is that it is very critical to perform on-device learning for a very simple reason. We already commented this morning that the inference is very, very memory and computing demanding, but the training is one more order of magnitude memory demanding and computational demanding. This means that I do not just need to reduce the complexity of the inference, but I also need to identify approximated learning mechanism to support the on-device learning. Okay, Luca?
Yes, it's clear to me, this one, yes. Yeah, you need to consider also the backpropagation phase.
Yeah, the problem with the backpropagation is the fact that you have to take all the activation and then go back. Yeah. Okay, yes. This is exactly the point that requires to perform, let me say, approximated backpropagation, meaning that you are only training part of the network and not all of them. For example, there are solutions that allow to keep to update only the weights. Sorry, only the bias and not the weights, because it is easier. Because in the bias, I don't have to take into account the effect of former layers. But obviously, this creates an approximation of on the training, meaning that you are losing in performance.
Okay, thank you very much.
Okay, well, you're welcome. Other comments, questions? Okay, so let's move to the active learning. Active learning refers to the ability to perform adaptation while integrating information coming from the field, information coming from the possibility to detect change. So if you look at the picture here, you see that we have sensors, we have the application, and in the middle, we don't have just adaptation. We have detection and adaptation, which is different from the passive approach where we had only adaptation. Here we have detection and adaptation, meaning that at first we detect that there is a change, and then we, according to the fact that we identify the change, we understand how to deal with this change. So, how can I detect that there is a change? I can do that in many different ways, and we will see them. But at first, I need to understand which is the figure of merit, where I am detecting the change, meaning that I have two different chances to detect that there is a change. At first, I can identify changes in the input. Let's take a look at the picture, the upper picture. You see that there is a data generating process that are generating X, Y, X2, XN, and so on and so forth. Then we have the classifier, then we have the output classifier. Okay, fine. But data X1, Xn, so the input data, the regressor, are evaluated by means of a change detection test. And here, if we detect that there is a change, then we adapt the classifier. Here, we are able to monitor the data even in unlabeled observation. So we are not required to have the supervised information. It's like saying if I have P, X, and Y, I'm looking at the distribution of the X. That's what I'm doing. So I'm not required to have the supervised information, but obviously this solution does not allow me to understand variations in the relationship between X and Y. Let me show you a very simple example. Let's consider that we have two classes, class A and B, that we have to Gaussian. Okay? If I'm looking just at the input, I look at the distribution of the Gaussians, so the value which are coming. But if at some point, for whatever reasons, we are switching the classes, so from the classes A becomes B and class B becomes A, the distribution of the inputs does not change. So we are not able to detect it because the distribution of the change is not affected by the variation, but here we changed the classes. So we changed the relationship between X and Y. So the advantage here is that we are able to detect changes, not looking only on supervised data, because we can do that on unsupervised data, but we are not able to detect variations in the relationship between X and Y. A different approach is the second one, which is the change detection on the classification error. Here, what we do is, as you can see, we have data which are popping in the classifier. We have the output, and then we have the supervised information. We can detect variations in the error, in the classification error, classification or regression error, whatever. If I realize that the error decreases, typically not increases. Sorry, if the error increases, typically not decreases, meaning that I'm recognizing the fact that the error, instead of being stable, it is increasing suddenly or slowly, then this means that there was a change in the relationship between X and Y. And this means that I can detect that there is a change, and I want to adapt the classifier accordingly. The advantage here is that I react only if I'm able, I'm detecting all the changes which are affecting the accuracy. And this means that I'm updating my classifiers for all the cases, for all the changes which have a direct impact on the accuracy. But the drawback here is the fact that I need supervised samples. Otherwise, this approach is not able to operate, meaning that I need supervised sample to compute the classification error. And how can we implement this active mechanism? Let's assume that we have some data which are coming from the field. Here, for example, we have the temperature sensors coming from the rock collapse forecasting system that I showed before. We have an application which is able to, I don't know, raise an alarm or to trigger an alert. We extract some features over time. Features means that we extract, for example, the mean value in batches of data, the standard deviation, the peak-to-peak distance, the energy. We have some features which are extracted over time. We introduce concept drift detection mechanism and adaptation mechanism, which are, at first, the concept drift detection is able to detect that there is something wrong in the features. And if there is something wrong, where something wrong means that there is a change in the statistical distribution, then we trigger the adaptation. What do we do typically here? We rely on an initial training sequence, which are assumed to be change-free. So we have some data, and then I will answer your question, Francesco, and I will take the last one. So any comment on reapplication? Let's think about the reapplication for stock market prediction with COVID. Okay, let's assume that we are in January 2020, so before the COVID appearance in Italy. Let's keep things simple. Let's think about Italy or Europe. We model a stock prediction regressor or prediction model. And then we use some data for the data coming from the 2019, and this is the training sequence. Then we extract some features peak to peak or to create a prediction model, and this is what you see here in blue. At some point, let's take the data of February 20, which is our data in the reference data here in Italy. We use the data coming from the training sequence to define a reference concept. So the reference concept, it's how the market evolves in 2018, 2019, so pre-COVID. And then at some point we say, okay, our prediction is pretty good, then let's try to move on the field. So we applied it to direct measurement. And so we started evaluating this mean value, standard deviation, energy, peak to peak. And at some point we come to February, 2020 here in Italy. And at some point we had the crisis induced by the effect of COVID. And then we saw that the stock market completely changed. We had huge drops in accuracy, and then we say, okay, stop. I see something strange in the data, and this the concept drift detection mechanism to tell us, okay, there is something anomalous in the data that I see. This is exactly change detection or anomaly detection technique. In addition to that, it could raise an alert to the adaptation, say, hey, I identified that there is something strange in February 2022. And I want also to provide information saying that, in my opinion, this strange behavior started 1 week ago. Okay, because I realized that there was something strange in the data, because the distribution of the data was not, let me say, stable enough since February 2013. And then what's going on is that, okay, I detect that there is a change. I could tell you when this change started, when we detected it, and then what I can do following the active approach is that I use only the last set of data from what I estimated that the change started. And the current time, I use this set of data to train a new model, which is becoming the new reference concept. And then we keep on operating, because on top of that, I could estimate many reference concepts, where reference concept means that we have many working modalities of our system. And then once I identify a new reference concept, then I can reactivate the concept drift detection mechanism, but on the new reference concept, and then the activation, and so on and so forth. So I keep on operating detection, adaptation, learning, detection, adaptation, learning. And I can do that by also creating a library of concepts which represent what happened in the past. It's like, say, I have a library of what happened in 2008, in 2009, when we had the financial crisis. I had what happened in 2020 with the COVID crisis, and so on and so forth. I keep a library of concepts about what's going on. Let me see the first question from Francesco. Suppose make assumption on the ratio between the time needed to properly estimate the PDF of X and the time needed to converge on good solutions. Are there some analysis on that? Yes, there are some specific analysis which takes into account not only the time, but also the dimension that I'm considering. Because I would say the larger the dimension of data, obviously the larger the amount and the largest the difficulty in converging to a good estimate. That's the reason why there are many, say, approaches. Some of them, when the dimension of the data does not scale too much, which try to use estimate of the probability density function, and then, for example, use a Hellinger distances or that type of approach to make comparison, or Kullback-Leibler to make comparisons of probability density function. But often, if the dimension of data scales too much, you don't want to estimate the PDF, because correctly estimating that PDF might require too much time, too much samples, in order then to be effective in the technique chain. And there you want to extract some features. For example, you want to identify variations in the mean value, variations in the standard deviation, or variation in the mode, or something similar. Okay, Francesco. Okay, sorry, let me see. Do you think distributional robust optimization learning can at least mitigate the need of adaptation? If so, to what extent? Okay, good question, Matteo. The answer is yes. It's strictly depends which is the technological perspective that we have. In the point of view that we currently consider is the fact that we must also pay attention to the amount of computation that we require for the learning. But in principle, having distributed approach, it's more effective in providing let me say, more data at the same time and different perspective of the same data generating process. From this perspective, I strongly, as Michele was saying, I strongly suggest you to attend the seminar on federated learning, because that's not exactly what you mentioned, Matteo, but it's a slightly different perspective, but very relevant, where you say that in a federated learning scenario, I have many workers which are trying to learn and optimize in a distributed way while guaranteeing the privacy and so on and so forth. And here, it is particularly interesting the fact that they continuously adapting, but if you want to converge, you have to reduce the learning rate, otherwise you don't have the the guarantee to converge. But if you reduce the learning rate such that you have the guarantee to converge to the optimal solution, you are then no more plastic in adapting, meaning that you have to balance and consider which is the trade-off between stability and plasticity. As regards Lucas' questions, how do you choose the best concept to use for predictions using instance weighting, selection weighting, or ensembling among them? If as regards the reference concept, here I'm using an approach where I have multiple models, but not at the same time. Here I'm using a single reference concept, and the reference concept is used as the one which is providing the largest accuracy on the recently acquired data. So it is not an ensemble approach here. I'm not using all of them at the same time. I'm using all of them historically, and I activate one of them every time I detect that there is a change. That's the main difference in the ensemble. So it's like having an ensemble, but with a voting mechanism that forces you to have just one single classifier, which is used up to when I change the voting mechanism. Okay, Luca?
Okay.
Okay, so let's see how can we implement this concept-driven detection. Let me say that these techniques are very general in the sense that they come from the point of the field of statistics. They come from the field of anomaly detection. So I think that it is worth to explore them and consider them for sure learning in association environment concept drift, but then can be used even in another application scenario. I don't know, full detection, detection of changes in the interest of user, just to name a few. So change detection. I want to detect changes, and this reminds me to the questions coming from, let me see, ask me that, from Francesco. Okay, change of what? Because this is crucial, because I can estimate a probability density function. I could do that, but we already mentioned that I suffer from the curse of dimensionality. I need a lot of data to correctly estimate the probability density function, and so on and so forth. So very often we resort on, let me say, approximation, meaning that we extract some features which are coming from the probability density function. For example, I could estimate, I don't know, mean value, the standard deviation. Obviously, I can simplify my problems, but I'm also neglecting all the changes which are not, which do not have an effect on the features that I'm measuring. Because if, for example, I'm measuring only the mean value of a probability density function, if the shape, if I'm modifying the standard deviation of the probability density function, but not the mean value, okay, I see that there is no change. But technically speaking, there is a change in the probability density function which I'm not perceiving by means of the feature that I selected. So we have always to understand which is the point of view. So which are the features that I'm extracting from my data in order to detect a change? At first, I can operate in the data space, so in the space of the data. What does it mean? This means that I can identify selected samples of data, so selected samples of raw data, which are particularly representative. Let me show you this example. If you look at the picture here on the left, lower left, you see the water flow in a DMA, so which is a district measured area in the area of Barcelona. So this is the amount of data which is used by that specific neighborhood. I mean, just to give you the flavor. Obviously, we have the largest amount of data during the day, and the minimum is during the night. So what I can do is to, and here, sorry, you can see that these are not IID data, because this is a time-dependent time series. But if I take the minimum value day by day, and if there is no change, we are expecting that these are ID over time. So as you can see, I can apply change detection on the minimum daily flow, so which is the minimum value day by day. And so I'm not applying our change detection to whole of data, but I'm applying the change detection to selected data, selected raw data, which are representative. So I'm able to transform them into IID. So I use raw data, which are IID, and then I can apply all the change detection mechanisms. The second approach is that I extract some feature, mean value, standard deviation, or the residual. What does this mean? This means that if I am a time series and I predict and I learn a model and I make a comparison, so I compute the residual, which is the discrepancy between what I predict and what I measured, then here I'm expecting that in stationary conditions, the data are IID. And so I can apply a change detection test on features like the residuals or statistical features abstracted from data. Or think about that, I could also apply change detection on in the parameters space, meaning that I take batches of data, I estimate, for example, a model, a simple model, a linear model, and then I'm applying a change detection test on the models which are estimated on the data. Why? Because there is a very nice theory, for example, that allows us to say that under very mild assumption, if I'm estimating a linear model, a linear input-output models on a time series, the parameters of these models are distributed according to a multivariate Gaussian distribution, which has some nice theoretical properties. But this allows us to say that if I take a time series, I divide it into batches, and I estimate an input-output linear time invariant input-output model. I take the parameters. These parameters follow a Gaussian distribution. So I can apply all the techniques which could be applied to Gaussian data. So,
Manuel, this is Michele. Sorry for interrupting.
Yeah.
This is a very nice approach, but I have a main concern is about the length of the windows that you use.
Okay.
That you use to estimate the parameter. Because if you are taking the windows that are too short, then the process is basically non-stationary over short windows, and you may have a large variance for the parameter.
The problem is the variance. The variance, is not. It is still stationary if the data is stationary. But
it's the variance of the parameter. Yes.
Yeah.
So the windows should be carefully, let's say, designed in order for those parameters to be stable over the windows, so that you can run this comparison as you suggested, in my opinion.
Absolutely, yes, Michele. And there is one more additional comment since we are discussing. The window cannot be overlapping, because otherwise you don't have IID data. Okay.
Exactly.
And if they are not overlapping, you have the problem with the connection, where you are partitioning your sub windows. And so this is an interesting point, meaning that you can do that here, but you have to take into account, let me say, reasonably good, reasonably large window. But you can do that. You can try taking subsamples, so subsequence, and then estimating the data, and then you can see if you can use a statistical hypothesis test to see if the data that you are estimated, which are the parameters, do fit pretty good a Gaussian distribution. And if it is true, this means that the size of your windows is reasonably correct. But I do fully agree with your comment.
Yes. Sorry for interrupting.
Thank you.
I just felt this was a good point to raise. Yes.
Yeah, exactly. So I can make a change detection in the data space, in the feature space, or in the model space. In all the cases, the idea is that I'm analyzing data, features, or models in order to detect as soon as possible variations in the data. How can we do that? Typically, what I can do is that I identify change detection mechanism and change point methods, and I will quickly describe them. Then, once I detect that there is a change, I have to identify the new state of the process. So I have to identify when the change started, and then I have to retrain the application by means of online batch of full learning. And this is exactly the what to do that we already seen. So let me enter into detail of the first and the second step. So detection and identification of the new step. So concept drift detection. this is exactly the models that allows us to identify that there is a change. So identify that there is a variations in the data generating process. One could say, okay, the first thing that I can do is that I put a threshold. When we don't know what to do, we put a threshold, and that's what we call the limit checking. I could have also a couple of thresholds, and then these are called the binary thresholds, and these are the data-based methods where we say, okay, I put a threshold plus 10, minus 10. If you're going above or below, I detect that there's a change. But then there are more statistically grounded techniques, which are called the statistical-based methods. And we will refer to statistical hypothesis test, change point methods, and change detection test. They are different. They share similar names, but they are significantly different. And then I will want to comment them into detail. But let's start with limit checking. Here, this is the easiest way, easiest thing that we can imagine, easiest thing that we can do. So I have a value, I set a threshold, I say if it goes above the threshold, I raise an alarm. Easy to implement, sure, but it's extremely, extremely difficult to set the threshold. Let me make a very personal comments coming from my expertise. Every time you see a threshold somewhere, please ask yourself, how do you set the threshold? Which is a problem which is much, much, much more complex than could be intended. Because if the threshold is too high, okay, you will perceive the change once it is too evident. While if the threshold is too low, you will have many false positive detection. But high and low, they are very difficult to be tuned. Why? Because in principle, you don't know the type of change that might affect the system. So you don't know that if there is a problem, your value, your mean value will go above 10. You don't know. You just know the nominal state. That's the reason why it is very difficult to set thresholds. Typically, what we can do is to exploit the fact that maybe we have, I don't know, two distributions, one for the nominal state and one for the nominal state, as in this case. If this is the case, it's like having a classification problem, because if I have a nominal state and if I have an anomalous state, I can set a decision boundary in the middle that allows me to compensate detection and false positive and false negative detection. But this is in principle is a good solution, but this has two drawbacks. The first one is that in order to apply this mechanism, I need to have information associated to the type of change. But this rarely holds in the practice, because if we would have all the data coming from the whole possible faults of our systems, okay, lucky you, because this means that you already know at design time all the possible scenarios that might occur in the system. But it's not a typical situation, because the system might evolve in unpredictable manner. And this is point number one. Point number two, when you make this approach, and this is exactly the approach that you typically have in anomaly detection, when you perform classification of anomaly states, is the fact that the anomaly and the nominal class are typically heavily unbalanced. So maybe you have 99% of the samples in the nominal state and 1% or less in the anomalous state. So it is extremely difficult to create these type of classifiers. But again, take into account that it is, even if I would have some data, it is typically difficult to have all the possible data coming from all the possible alternative cases that might occur in a system. That's the reason why what I typically suggest is not to try to transform the change detection in a classification problem. Let's try to keep it as let me say, in some cases it could be a one classification problem, but let's try to focus only on the nominal state. And then we are looking for variation with respect to the nominal state. Here we can introduce the techniques that allows to that. So detect variation with respect to a nominal state, and detect variation with respect to data which are referring only to the nominal state. Here we have several types of techniques. The first one is the statistical test. The typical, the Z-test, the T-test, are all the tests that you might know which perform a statistical analysis of data. Let me clearly state that these are great tests. We have a solid theory to do that. but we cannot use that in an online manner. Why? Because the statistical test, what you can do is that you set the confidence, you say, I want to be sure that the mean value of this data is 0, and then you set the confidence of 95% and so on and so forth, that these are meant to perform a one-shot approach. Because if you say that the confidence is 95%, so you are assuming that there is an error of 5%, if you are repeating this test 100 times, you will have structurally 5 false positive detection over the 100 times that you are using in stationary conditions. So statistical tests are great because that's what we learn in our statistical courses, but they cannot be applied in an online manner. That's the reason why they can control false positive, which is great, but they cannot be used. They can be used in an offline manner, and they cannot be used in an online manner. That's the reason why we have to typically resort on change detection test. Since I'm running out of time, let me skip the slide about the statistical hypothesis test. I'm pretty sure that you know about the statistical hypothesis test, Z-test, the Mann-Whitney. There are tests which allows to identify the specific value of specific features, or there are tests which allows you to compare the mean value of 2 sets of data, or the empirical cumulative distribution in 1D of the test. But again, these are great, but they cannot be used in an online manner. They can be used one single shot, so in an offline manner. The extension of the test, of the statistical hypothesis tests, are the change point methods. The change point methods integrate the fact that you are repeating the hypothesis test over time, but only on a given subsequence of time. So you say that I have, I don't know, 1,000 samples, and you ask yourself, is there a change somewhere within these 1,000 samples? It's not online. You have the fixed 1,000 samples, and then you say, I'm not sure if there's a change, but if there's a change, I want to know, where is it? And so what you do, and here you see the technicality of change point methods, is that you try all the possible partitions. And then you say, I tried 1, 99, 999, and then 2, 998, and so on and so forth. You take all possible partitions. This is a repeated statistical hypothesis test. I'm taking into account the fact that I'm repeating this test, and I can do that. And what I can compute is the fact that, as you can see here, this is an example. On the upper plot, you see the data. On the lower plot, you see a figure of merit, which is the discrepancy in the mean value in the 2 partitions, and every point in the lower figure represents a partition. So 199, 298, and so on and so forth. You take the upper value of this figure of merit. If it is above a threshold which can you empirically compute, you say, at first, there is a change, one single. There's a change in this sequence, and where is it? This is a change point method, which is a repeated statistical hypothesis test, but it is not truly online, because you have to fix the set of data on top. You can apply the change point method. So these are very useful when you have, okay, did something happen in the last year or not? Which is not an online analysis. It is fixed because you are just looking at the last year data. I want to then move to the third family, which is the one that we currently actually using to detect change in an online manner, which are the change detection tests. The change detection tests are statistical techniques that designed to identify, to detect variations in the process, in the probability density function of the process generating the data over time. Obviously, these are more complex than statistical hypothesis tests and change point methods. We have some tests which are really effective. The problem here is that we cannot a priori control the false positive detection. We can empirically compensate them. And here we have 3 main families of approaches. We have the parametric approach, where we know the probability density function before and after the change, meaning that I know that the nominal state is this PDF. I know that the alternative state is this other PDF, and so on and so forth. And the most and widely used technique is the CUSUM test. This is which is the cumulative sum test. And then you have the solutions which are the non-parametric approach, where you don't know neither before and nor after the change the probability density function. So you have to estimate from data. And then there are some approaches where you can partially know the probability function before and not after the change, or not after the change in a set of viable solutions. Let me give you the flavor about the CUSUM test, because it is very nice and it is a very theoretically grounded test, which is really worth to be explored. Which is the idea? The idea is that at first, let me remind you that we are assuming that we know the probability density function before and after the change, which is, in this case, we have a p theta 0 and p d theta 1, which are the parameters theta 0, theta 1 before and after the change. So what we typically do is that we are computing this log likelihood in the squared box here. We receive the data, we say it is more likely which has been generated by theta 1 or theta 0. And then we compute this figure of merit, we integrate, and since there is a log, if it is more likely that it is from theta 0, we are going down. Okay, if at some point it is more likely which is from theta 1, we are going up. Okay, and then what we are detecting is we are integrating this cumulative value over time, and we have to set a threshold. And again, there is a threshold here, but this threshold is, let me say, allows to theoretically know which is the amount of, so it is theoretically tune the false positive rate with the detection delay, which is the time which is associated to detect a change. So it is a very nice test, very theoretically grounded. The problem is that it is a parametric test. So in order to use it, we have to know the probability density function before and after the change. Before the change, I would say it is viable. We could approximate, but after the change, it is a strong assumption, because this means that we have to know exactly where the system is going after the change. I will skip some slides, but there are techniques that allows to extend the CUSUM test by means of estimating the parameters over time. And this is the computational intelligence CUSUM test, where here what you can see is that the log likelihood ratio is not done on the original value, but it is done on the transformed value associated to some say on-the-fly learned probability density function. There are also some techniques which are able to operate on the intersection of intervals. So what we do is that we can transform this change detection problem into a regression problem, and then we want to be sure that we are estimating some parameters and that these parameters remain stable over time. And we do that by considering the intersection of confidence interval rule, which is a method which allows to perform adaptive estimates for regression of function. And when, so you are, for example, estimating the mean value of something, and then while you are estimating over time, you are reducing also the variance associated to that estimate. But at some point, if there is a change in the mean value, then the intersection between the estimate and the associated interval is no more valid, and then we detect that there is a change. Okay, what is the point here? The point is that whatever the technique that you are using, you can then tune the parameters in order to be more effective in detecting change. So reducing the detection delay because you are prompter in detecting the change, or you are less prone to false positive detection. Obviously, this is a trade-off. If I want to be very prompt in detecting change, I pay, let me say, cost in the fact that I might occur more likely in false positive detection. And differently, if I want to be very low false positive detection, I'm also introducing a delay in the detection. So the problem is, how can I have a very effective change detection test to be prompt in detecting while granting low false positive detection? We have to understand not only what happened, but when something happened. So let me show this example, and then I'm going to the end of my presentation. Let's assume that this is data generating process. We are using the data in yellow for the training. Then the blue points are the data which are receiving over time. At some point, we detected the change is introduced at time t star. So we have a change in something. Here, for example, increasing the mean value. We need some time, because we know that we need some time to detect the change, and we detect in the red line, which is where we detected the change. We need some time. Why? Because if you remember here, and in the Kusum test, we have a threshold. And if there is a threshold, we need some time to overcome this threshold. So we are not able to immediately detect that there is a change. We need some time. But once I detected that there is a change, then I could say, okay, now there is a change. But since I know that I have some delay, let me see when the change started. So I could try to perform an estimate on when the change started. And to achieve this goal, I could resort on, for example, the change point methods, because I could apply a change point methods from T0 to T hat and say, okay, I know that something happened. Please tell me when we had the problem. Okay. And so I could have an estimate on when the change started, which is Tref. Obviously, the closer Tref to T star, say the better. Because in this case, what I can do is that I can perform a second level analysis between Tref and T hat, just to say, okay, what happened? And this is the hierarchical change detection test, where I have a very prompt change detection mechanism. But when I detect that there is a change, I want to be truly sure that there is a change. I perform an estimate on when the change started. I take all the data from when the change started, estimated, and when I detected, and I perform a further level of analysis to reduce false positive detection. And I can do that by means of hypothesis test or change point methods. In this way, what I can do is that I identify that there is a change. Okay, this is the set of data that I identified as the new set of data, because I say, okay, I detected a change at time t hat. I identified at time tref that the change started, and all the samples between tref and t hat, they represent the new set of data. And on top of that, I can update the reference concept, I can adapt my classifier, and I can reactivate the triggering mechanism. So the data between Tref and T hat represent the new concept. And on top of that, I will update my classifier, and I will be able to continuously updating over time. And this is exactly where the just-in-time adaptive classifiers come into play, where we have the data which are coming from the field. We have the ability to detect changes by means of a hierarchical concept of detection. We have the ability to adapt over time by means of exactly this mechanism. So detect that there is a change. Once I identify the data which are associated to the new state of the process, I create a new concept, and then I keep the recurrent concept in the next future, because when I detected that there is a change, I estimated the new state, and I want to also understand if this new state is exactly the same that I had in one of my previous concepts. And in this way, I can merge and trying to overcome the problems that I have always to start from scratch with a new set of data. Because in this retraining phase, the main problem I have to face is the fact that if I'm very prompt in detecting phase, the distance between Tref and T hat is too close to create a new classifier. And this is particularly crucial, for example, in deep neural network, where I have very few samples between Tref and T hat. But again, the idea is that I want to exploit the recurrent concept, and in this way, I'm also able to exploit recurrent concept, which is exactly this example where I move the scenario from one classification problem to another one, and as you can see, I'm updating my classifier over time, but at some point I'm refacing a classification problem that I previously explored, that I previously learned. What I want to measure, what I want to comment is the fact that these adaptive classifiers have very nice theoretical properties guaranteeing the asymptotic optimality when the process generating the data is affected by a sequence of abrupt constant drift, where abrupt means that there is a sudden change from one probability density function to another one. Under this mild constraint, this just-in-time adaptive classifier guarantees the asymptotic optimality. I want to conclude with okay, I skipped this slide. I want to conclude this with this one, which refers to the fact that it is really important in all the, let me say, background of all the machine and deep learning expert to have some flavor or to have some expertise in the area of learning in association environments or learning in presence of constant drift, because we have always to deal with the process generating the data which evolves over time. And the second comment is that we typically, or if you look at the literature, and I strongly encourage you to, next time you will read papers, a very nice paper coming from the literature, please try to see if the IID hypothesis is explicitly mentioned there, or if they say that the data are IID. Because if not, you have to ask yourselves, does this hypothesis hold or not in real situations? Because we often apply that allows us to understand whether what to do when this assumption does not hold. And the third point, I would say last but not least, learning in changing environment, in presence of constant drift, is a key ability for all the intelligent systems which must operate in the real situation. And this exactly refers to what we discussed in the previous lecture, when we said that I want to move my system in the real world. And if my system has to learn in a time-varying scenario, as typically the world is, this system must be endowed with this technique. Yes, Michele, I have at the end of this presentation, I have some references there where the adaptive constant drift are analyzed. There are very, very nice survey papers that you can use. And let me say one point which is still fully missing. I say that to Michele and to everybody. There is no, there is still a room for a theoretically grounded analysis of learning in presence of constant drift, because it is a very tough problem in terms of convergence, unless in very tiny scenarios, like for example the one that I mentioned for the just-in-time classifiers, where you can prove the convergence. But there are no general rules, general theory for all the possible types of change and all the possible types of learning mechanisms. So there is still rooms to advance the theory in this field, and that's the area in which we are working with.